Hi class, in this discussion we're going to be focusing on action potentials. And when I think of an action potential, I want you to think of sending electrical signals down the length of an axon. So when we think of action potentials, a lot of times these are just going to be referred to as an electric signal. A more formal definition of an action potential is that it's a dramatic change in membrane voltage or membrane polarity changed as ions are moving in and out of voltage-gated ion channels. And we're going to spend a lot of time talking about that term, voltage-gated ion channel. A voltage-gated ion channel, we'll talk about in more detail, but the name pretty much says it all. It is a channel in a membrane that lets ions go in and out, and it opens and closes based on a change in the voltage of the membrane. So as we're looking at these action potentials, we need to have a very high density or high concentration of voltage-gated channels for voltage-regulated gates. Our neurosoma, the cell body of the neuron, has a low density of gates. So 50 to 75 gates per square micrometer. And then when we look at the trigger zone, which is the very first part of the axon, we can have up to 500 voltage-gated channels per square micron or micrometer. And this is where action potentials are generated. These action potentials are going to depend upon excitatory local potentials converging. We need enough excitatory local potentials converging at the trigger zone. And if we get enough excitatory local potentials, we'll open up enough gates and ultimately generate the action potential. So as we're looking at this process of generating the action potential, here's a better spot. I wish I could make this icon smaller. So as we're going through this process of generating the action potential, we're going to have a rapid change in the membrane voltage. And there's going to be some sequences or some steps involved. First, we're going to have the arrival of current. When I say current or electrical current, I want you to think of the movement of charged particles. So we're going to have sodium and potassium ions moving around, and we'll have a lot of movement of charged particles at the axon hillock. So here we are at the very beginning. Here's the axon hillock. The current has not arrived yet, so we're at resting membrane potential, that negative 70 millivolts. And note the sodium voltage-gated channels are closed and the potassium voltage-gated channels are closed. We need to reach a threshold voltage. Typically for a motor neuron, it's going to be about negative 55 millivolts. And once we hit that negative 55 millivolts, the sodium voltage-gated channels open up. So bloop, bloop, they open up. And we're going to start to have sodium ions from the extracellular environment rush in to the intracellular environment. And as we have positive ions from the outside rush to the inside, we make the inside of the cell more positive. And look at this little voltage graph over here in the corner. Notice how the red line is going up. We're having an increase in voltage on the inside of the membrane. So when these voltage-gated channels open, sodium ions enter and depolarize the cell or make the inside of the cell more positive. And this is a positive feedback cycle. Once the inside of the cell starts to become more and more positive, that causes more and more sodium voltage-gated channels open, which lets more sodium in, which means more sodium voltage-gated channels open. This happens nearly instantaneously. It's a very, very fast process. So we just talked about how we have that resting membrane potential, and then the local potentials converge at the axon hillock. They reach the threshold voltage of negative 55 millivolts. Once we reach threshold voltage, we're going to have sodium voltage-gated channels open. Sodium ions are rushing in as the inside of the membrane becomes more and more positive. And now we need, at this peak voltage at about positive 35 millivolts, sodium voltage-gated channels become deactivated. So let's talk through that process. As our membrane potential is rising up or raising up, this is 0 millivolts, sodium voltage-gated channels start to close, and then at this peak voltage right here, our sodium of 35 millivolts, sodium voltage-gated channels will close off entirely. So here we see that sodium voltage-gated channel closed off, but at positive 35 millivolts, potassium voltage-gated channels open up. And now we have positive potassium ions on the inside of the cell rushing outward. So the inside of the cell is now going to become more and more negative. And we watch, if we look at the graph here in the corner, notice how the voltage is now going down and it's decreasing. And that voltage is going to continue to decrease until we reach a hyperpolarized state. And that hyperpolarized state is going to be more negative than resting membrane potential. So many potassium ions rush out of the cell that we lose those potassium ions. The cell membrane becomes hyperpolarized, and at that hyperpolarized state, the potassium voltage-gated channels close. So now the voltage is almost back to normal, but the ions have been all moved around. A bunch of the sodium ions rushed into the cell, a bunch of the potassium ions have rushed out of the cell. Concentration gradients are all kittywampus. To get our concentration gradients of potassium and sodium back to the original state and get back to our resting membrane potential, we're going to use sodium-potassium pumps. And that sodium-potassium pump will move 3 sodiums out of the cell and bring 2 potassiums into the cell. We're also going to have sodium leak channels and potassium leak channels as well at play. The sodium-potassium pump, though, is the single most important thing for restoring that resting membrane potential. So here at step 4, we have sodium voltage-gated channels becoming closed, potassium voltage-gated channels open. Here at step 5, potassium, I'll put a K for potassium, K positive, rushes out. The voltage decreases until it becomes hyperpolarized at step 6. And at step 6, potassium voltage-gated channels close. And to go from step 6 back to step 7, the resting membrane potential, we are primarily going to focus on how the sodium-potassium pump brings the concentration gradients back up to the starting concentration gradients. So, as we're looking at this action potential, it's only a very, very small layer of the cytoplasm right next to the cell membrane, the neurolemma, that is really going to be affected. And very few ions are involved. I know the diagrams I showed make it seem like there's tons of movement of ions, but compared to the total number of ions in the cell, there's actually a very small movement of ions. And this action potential can be referred to as a spike in voltage because it happens so fast. That slide I showed you, or that figure I showed you on the last slide, really overemphasizes the time differences. I need to emphasize for you that action potentials are an all or nothing event. Once you reach that threshold voltage of negative 55 millivolts, we're going to have the entire action potential. We're going to go up to positive 35 millivolts and go through the whole sequence of events. If we do not reach the threshold voltage of negative 55 millivolts, there is no action potential. It's an all or nothing event. We'd never have halfway or half action potentials or partial action potentials. It's kind of like being pregnant. Either you're pregnant or you're not pregnant. There's no partially pregnant. Now, when we look at this action potential, it is non-decremental. So it does not get weaker with distance, which is different from a local potential. Local potentials are decremental. They decrease over distances. Also, action potentials are irreversible. Once they start, they have to finish. There is no stopping it halfway through the process. So let's go back to our figure here. This figure here overemphasizes the differences of the voltage changes as the channels are opening. But this figure on this side of the screen is a better figure because it's drawn to scale in terms of time. So what we see is that we have negative 70 millivolts at time 0 milliseconds. There's a giant spike in voltage. It goes down immediately. And then that hyperpolarized state typically goes from 5 milliseconds all the way up to 50 milliseconds. So there's about a 45 millisecond time frame where it's hyperpolarized compared to everything else of the action potential taking place in a period of about 5 milliseconds. And that's all we have for this recording. Action potentials are kind of a tricky topic. I want to encourage you to read the textbook chapter on action potentials. It's pretty beefy. If you have any questions, please feel free to post them on the class discussion board. And as always, happy studies.